Good morning, students. So please type in the chat box. Am I audible? Yeah. So please type in the chat box. Am I audible? Is it audible? It's audible, right? Yeah. Okay. All clear. Great. So in this lecture, basically we'll try to introduce external flows. But before going for external flows, we will complete that control volume RTTs and also this internal flows. Okay. So once we finish off these things, then we will slowly keep into this external flows in today's lecture. And in today's lecture, the main topics will be Reynolds transport theorem and applications, and also Navier-Stokes equation. We'll see how this equation actually turns out. Of course, our interest in this course will be only for incompressible flows. Okay, so we will see this Navier-Stokes equation, and also actually we'll see that this equation is very difficult to solve. Even this don't have a solution till today, but we can see some simple flows like Couette flow, plane Poiseuille, Huygens Poiseuille. These kind of flows we can see, and we can understand that we can actually derive expressions for certain simple flows. Okay, and all over we'll solve numericals at every topic. Okay, so this is how the flow of today's lecture is going to be, and if time permits, we'll also have certain introduction to some external flows in this case. Okay, now in last class, if you see carefully, we have talked about Euler's equation like rho x bar minus del p is equal to rho times dv by dt actually. Okay, so this is the Navier-Stokes equation that you have, and sorry, this is actually the Euler's equation. And if you apply this Euler's equation along a streamline, this gives you Bernoulli's equation, correct? So applying this Euler's equation along a streamline gives you Bernoulli's equation. We have seen certain assumptions we have made. The flow is steady. Then we have seen the flow is incompressible, inviscid, irrotational, all these things we have. Of course, irrotational is again a very special case that we have to check whether the flow is irrotational or not before applying Bernoulli's equation. If the flow is irrotational, you can apply Bernoulli's equation at any 2 points in the flow. But if the flow is actually rotational, then definitely you can apply Bernoulli's equation at 2 points on the same streamline. Okay, so we can understand all these things. And from here, we have also moved to Bernoulli's equation like P by rho z, kinetic head plus, sorry, this is the pressure head plus kinetic head plus potential head is actually constant. Okay, so we have seen this. Now we have solved 1 and 2 questions on based on this Bernoulli's equation in last class actually. And also you can see normally can have using this Bernoulli's application, you have a lot of applications like applications of Bernoulli's. You have plenty of applications, but one of the very important application is flow measuring devices. Then after velocity measuring devices, you can generate velocity measuring devices. Okay, and we have again plenty of like applications like pressure measurement. You can do using these principles of Bernoulli's equation. You can design certain pressure measurement devices. So basically here in this case, flow measurement is like your Venturi, for example, Venturi meter. You can also have an orifice meter, and generally the flow nozzle meter is also to a certain extent we smoothen the orifice. So flow nozzle meter actually. Okay, and coming to velocity, we have static pitot tube, Henry's pitot tube. We can generally design some pitot tubes, and some devices you can actually design here. Okay, which uses the help of Bernoulli's equation to calculate the pressure directly. Okay, so we can see, and of course, do you have a clear idea about these things, Venturi, orifice? Because the calculations are very simple actually. If you just take a Venturi meter, like for example, I'll just show you for one case. If you have a pipeline like this, okay, then you can have a Venturi converging part, then you have the throat, then you have the diverging part again, and again you have the pipeline. Means basically in a pipeline you will actually rupture at 2 locations in order to study the flow. Okay, and what you will do, you will actually connect these 2 edges by a manometer. Okay, so what you will get is actually you will connect this using a manometer. Like this. Okay, and correspondingly due to the pressure difference, what we can see in general is the liquid level can actually show certain difference in the manometric fluid. So if this is actually your manometric fluid, density of manometric fluid, and normally if some fluid is actually flowing inside, okay, so some fluid is actually flowing inside. Okay, so I'm just drawing some sketch, it's flowing inside. Okay, so this is actually a 𝐁𝐴 meter. Normally it is designed by an Italian physicist called 𝐁𝐴, so that's why we call this as a 𝐁𝐴 meter, which can actually measure the flow directly. Okay, good morning. So if you see, you can calculate using this deflection H, using this deflection, manometric deflection H actually, and by knowing the dimensions of the 𝐁𝐴 meter, like for example, whatever is the pipe diameter, same will be the inlet area here. So this is A1 for example, and this area here is A2, which is actually the throat. Okay, so throat in this case, this is called throat, so we call this A2 as AT sometimes. Okay, so this A2 is called AT, and we can actually calculate what is the amount of flow which takes place through this 𝐁𝐴 meter by using continuity and also momentum balance. Okay, so for incompressible flows, as I told you, when flow is steady, we'll see using RTT again, the continuity equation can be reduced to rho AV at any section is equal to constant. Okay, so for example, if we call this A1 and A2, rho 1 A1 V1 is equal to rho 2 A2 V2. Guys, I want to tell you one thing here. Have anyone observed intentionally I have drawn this a smaller part and I have drawn this a larger part? Can you observe this in this diagram? It's not like I have drawn it accidentally, but actually there's a very big logic why 𝐁𝐴 meters are designed in this way. If you go into a bit of mechanics part, have you seen, can you understand that this part is actually short and with a higher cone angle, and this part in the diverging section is actually a higher part, it is of generally of some large length actually. Have you noticed this? Yes or no? Please type in the chat box. No, you haven't noticed? Fine. Here, but can you see now? Can you see that this part is actually short and having a higher cone angle, and this part is having generally a lesser cone angle and also a bit large in this case? Do anyone know what is the advantage of doing this? Normally if you see 𝐁𝐴 meters are actually like this. Okay, I'll show you basically by taking one of the 𝐁𝐴 meter. You might have seen, no, in your college labs and all. Have you never noticed both sections will not be same? There will be certain dissimilarity between those two. Okay, here for example, this is a YouTube animation I guess, but you can see, yeah, electrical workbooks, or in any case you can see, for example, this is fluid mechanics 𝐁𝐴 meter. You can see clearly this is a horizontal pipe fitted to a horizontal pipe. Can you notice one thing, that this part, I think the video is clear, right? Yeah, let me slightly reduce the brightness so that you can see. Yeah, okay, so now you can understand one thing. This part is having higher cone angle and a bit short in length, and this diverging part is generally a bit large in length and having a lesser cone angle comparatively. Can you understand why? Can anyone tell me why? What happens if this do? Because this is one of the standard questions in interview. They'll ask you, can you connect a 𝐁𝐴 meter in any direction? Okay, to compensate losses? No, actually losses will be there definitely, but the actual reason is not to compensate losses, it's beyond that. I'll tell you, see here. In interviews, one of the standard questions is, look, normally this is a single pipe, yes or no? In a single pipe, you actually cut some portion of the pipe and you attach your 𝐁𝐴 meter, normally with the help of flanges. Okay, in college, have you seen the 𝐁𝐴 meter? Have anyone done experiments on 𝐁𝐴 meter? In fluid mechanics labs, definitely might have done. Yes? Good morning, Dipanjan. Yeah, you might have done, right? But have you never questioned? Why? Lab means just go, enjoy, time pass, play with water in fluid mechanics lab, come out of the lab, go to canteen. Correct? This is how college life goes with fluid mechanics lab. But actually there is a lot to learn in the fluid mechanics lab. Actually if you see, yeah, it happens, I understand, because the same thing I have done when I was doing my fluid mechanics labs. Okay, cool. Because water will be coming, so play like you have gone to a resort, sprinkle water on each other, then enjoy and come back. Correct? Yeah, get. So see here. Basically one interview question is, normally you take a straight pipe of uniform diameter D, you cut some portion of this pipe and you attach a 𝐁𝐚𝐿 there, okay? And attaching this 𝐁𝐚𝐿 and correspondingly have a glass tube and correspondingly have a manometer, then how you can actually calculate the flow rate? First thing is the diameter here, just a minute guys, yeah, the diameter here, which is basically this opening, and the diameter here, they'll be same, correct? Because it should be adjusted to the same pipeline actually. Now, but in many of the cases you can see, or in all cases, you cannot connect this 𝐁𝐚𝐿 in the reverse direction, okay? Or even you can connect actually if you want, mechanically you can fit using flanges, but actually in fluid mechanics point of view, you cannot do it in this way. The reason for that is, look, I'll tell you. Let us suppose if a flow is happening, then in a direction, let us suppose I'm reducing the cross section, okay? So if I am reducing the cross section, then this flow will accelerate because of the convective acceleration. You know, acceleration is equal to dou u by dou t. Okay, if I take only one dimensional flow, for example, you know, things are steady, so this term will get vanished, but this term will sustain because there is a gradient in this direction. Yes or no? As the fluid particles move in this direction, the fluid accelerates, okay? So when this fluid accelerates, then understand one thing here. If you connect this pipe in this direction, let us suppose if this cone angle is high relatively, if this cone angle is high, normally it's 12 to 15 degrees roughly. So if this cone angle is high, this high cone angle end, if it's connected in the upstream direction, this high cone angle end will actually facilitate, or it accelerates the flow, and this high cone angle in the upstream will actually creates a favor pressure gradient, because if dou u by dou x is increasing, then definitely what happens, your pressure will actually decrease in this particular direction because of, again, Bernoulli's equation, and this upstream high cone angle will actually facilitate, or it actually supports the flow to happen. Yes or no? Correct? Can you understand this? This high cone angle presence in the upstream will actually facilitate, or it actually pushes the fluid very effectively so that the flow happens in a better way in this case. Clear? Maximum, okay? So 15 is generally 12, it varies by 1 to 2 degrees depending on applications and accuracy, but that's the values. Can you understand this? The effect of this high cone angle? This high cone angle will at the upstream direction will actually facilitate the flow to happen effectively, okay? And second point here is, let us suppose if you have connected the 𝐁𝐚𝐿 in this direction, fine, the flow, this nozzle or this particular part, diverging cross section, if it comes to this side, it becomes converging, you will have a lesser cone angle part in the fluid, so this facilitates the flow less as compared to this case. Second, at this downstream direction, normally the fluid actually decelerates here, correct? The fluid actually decelerates, you know, the fluid actually will decelerate. Of course, the continuity equation still holds good, but if you compare the average velocity at this section and at this section, if you take 1-2 sections, then at this section, V average at second section is actually less than V average at the first section, correct? You know this. Now let us suppose you are talking about a horizontal pipe, horizontal 𝐁𝐚𝐿, for example, for easing. If V average 2 is less than V average 1, definitely compared to this point, at this point, the pressures, there's a chance. In actual case, it don't happen because of the losses. But when you're doing this analysis, you can understand this pressure will be actually greater than compared to this pressure actually. Yes or no? Or in the real case, because of the losses, the pressure difference between these two becomes small. If pressure difference between these two becomes small, then they start creating adverse pressure gradients. Means it could be possible. Theoretically, you can see if there are no losses, dou p by dou x is actually greater than 0 in this section, okay? But when you keep a higher cone angle here, let us suppose if your cone angle is high, for example, if you connect it in reverse way, and if the cone angle is high, this V average or the convective deceleration actually, because this acts as a diverging section then, so convective deceleration will be very large, and if convective deceleration is large, this adverse pressure gradients are also very large in the upstream direction, okay, sorry, in the downstream direction, okay? So which again try to push back the flow into the throat in this direction, okay? So because of all these technical points, we make one end at higher cone angle and one end at lower cone angle, and we make sure that high cone angle is always connected in the upstream direction and lower cone angle is connected in the downstream direction. Clear? Did you understand these points? Okay, yes or no? सबको समझ में आया या नहीं? Yes? Can you understand these logics behind everything? Okay? Fine? Yeah. These accelerations will actually create some pressure gradients which could favor and also oppose the flow. That's it, one word, okay? Now anyway, coming to our story, because we have a lot of story to cover today. Then what we can do, okay, I hope you can understand this. This 1 2 we are eliminating as of now, because we'll take the 1 2 at some other spots. Fine. Okay, now if you apply this Bernoulli's equation at this point A and also at this point B, did anyone get a doubt why only at these 2 points the 𝐂𝐴 is connected? Why not somewhere here or here maybe? Any idea? Yeah, I'm repeating. If you connect this high cone angle here, first of all, means if you have a configuration like this, and if the flow is happening in this direction, since this cone angle is less, when the fluid is approaching the convective acceleration, or what is the meaning of acceleration? The particles which are here are trying to move in this direction highly, okay, effectively. So this effect of accelerating the particles will be less as compared to this part, because here within a short span the fluid particles has to highly accelerate, okay. So connecting this high cone angle in the upstream direction will actually increase the flow, okay. And secondly, in this at the downstream direction, whenever the cone angle is high, the fluid decelerations, means that particles get slowed down by very much, so that it could be possible pressure increase and the adverse pressure gradients could develop actually in this particular locality, okay. So that's why we generally don't go for this particular configuration, rather we go for this configuration, okay. Yeah. Now can anyone tell me why exactly at these 2 ends it's connected but not somewhere here or here? Maybe one of the limb can be connected in the downstream direction or maybe in the upstream direction, but why it's not done? Because actually if you see, if you connect this here, the pressure fluctuations here could be present because of the fluid not moving uniformly, yes or no? In these 2 sections, in the third part and also in the pipe part, the fluid moves uniformly, but whereas in this converging and diverging sections, your fluid actually suffers certain acceleration or deceleration, which could actually change the pressure. So because of the pressure fluctuations and acceleratings, these readings may not be very accurate, okay. So that's why what we do, we connect these 2 in the locations where there is uniform flow, okay. You can in fact connect this here and also this edge here, okay. You can do that, but you should connect only at the uniform uniform flow points actually, okay. That's why. Now let us see, if you apply Bernoulli's equation, then you can easily get into the things. Okay, so let's get into certain things. Now if you want to calculate flow rate, Q dot is equal to discharge A1 V1 or maybe A2 V2, for example, okay. So let us suppose if this is section 1 and here it is section 2, okay. So A2 V2 is what you can say, and to get this A1 V1, let us suppose if you apply pressure equation, P1 by OZ plus V1 square by 2Z plus Z1 is equal to P2 by OZ plus V2 square by 2Z plus Z2 actually, okay. So plus Z2. Now you can understand something. This normally this is called the static pressure difference, and this is the potential because of the elevation, okay. If the 𝐂𝐴 is not, or if the pipeline is not horizontal, then this Z1 minus Z2 is not equal to 0, okay. So this P1 by OZ plus Z1 is actually called P1 star by rho z, and this is called piezometric head. Piezometric head actually, okay. So piezometric head, which we will see in due course. So this is called piezometric head, and if you apply certain equations using this manometer, if you bring out the pressure difference between these 2, and if you calculate, you can actually calculate what is this V1 or V2 accordingly from this equation, okay. So from this particular Bernoulli's equation, and you can get the expression for Q. This is, as far as I remember, normally I'm very bad at remembering, but I hope I write this correct, A1 square minus A2 square into square root of 2GH, H is the deflection, manometric fluid by this fluid minus 1. Is this expression correct? I think this is what you will get finally if you do certain calculations. It's very simple. Normally in this Bernoulli's equation, you will calculate this pressure difference is equal to in terms of velocities, and pressure difference you will also get from this manometric deflections. So if you substitute this manometric deflections, this pressure difference and velocities will actually give you this relation. Yes? Is this the relation that what you get? Yes or no? Only root 2GH. No, this should be there, no? Oh, manometric fluid by density of the fluid minus 1 should be there. Only root 2GH inside the root? I think no, actually. This also should be in the root, inside the root, I guess. Correct? Because the reason for this is this completely is the manometric pressure difference. Okay, so if this is the complete difference, if P1 star minus P2 star is taken as V2 square minus V1 square, definitely when you take the square root, okay, square root comes for this complete thing. Cut. Is that what we have? Shall we do quickly to identify this? Yes or no? Shall we do quickly what's happening here? Fine. Can anyone confirm me this expression? If not, then we'll derive. Okay. Anyway, I think nobody is responding, then we'll derive. So P1 by OG plus V1 square by 2Z plus Z1 is equal to P2 by OG plus V2 square by 2Z plus Z2. Okay. Then let us suppose if this point is at elevation of Z1, for example here, and this point is at elevation of this point here is at elevation of Z2, for example. Okay. Now if this is at Z2, then let's see P1 minus P2 by OZ, or P1 by OZ plus Z1 minus P2 by OZ plus Z2 is equal to V2 square minus V1 square by 2Z. Okay. Then from continuity you can have A1 V1 is equal to A2 V2. Then you know V2 or V1 can be written as we'll calculate A2 or V2. Anyway, it's fine, you can calculate anything. So V1, let us calculate V1. If you calculate, we have A2 by A1 times V2 actually. Okay, so this is A2 by A1 into V2. We'll substitute here, but first of all let us try to get something from manometer. So from this manometer you can see pressure at this location. For example, if you call this X, okay, then correspondingly you call this as X. Okay, not till here, this point. Look, you have the manometer. So what we can do is till this particular point you call this X, then this limit is Z2 minus Z1 clearly. Okay, this is Z2 minus Z1 here because this point is at Z1 and this point is at Z2. So the elevation difference between both those points is Z2 minus Z1. If we take this as X and if this is H, then let's see what we have. P1 plus, okay, so pressure at location 1 plus density of this fluid into G into X plus H. Density of the fluid into G into X plus H. So this density of the fluid actually. Okay, so G times X plus H is here. So pressure at this point should be same as pressure at this location. So pressure at this point is P2 plus rho FG Z2 minus Z1 plus X plus rho manometric fluid GH from the manometer. Okay, from this manometric balance rho m GH is what we have. So if you simplify this X and this X gets cancelled on both sides because rho FG is the multiplication. So this gives you P1 by rho FG plus H is equal to P1 by rho FG plus H is equal to, okay, so this H is equal to, then we have P2 by OZ plus Z2 minus Z1 plus rho m by rho f. G gets cancelled into H. Okay, so you can see P1 minus P2 by, or P1 by OZ, P1 by rho fluid Z. This minus Z1, if it comes here, it is plus Z1 minus, if these two terms comes to the left hand side, P2 by OZ plus minus, yeah, this is plus, then this is Z2 is equal to rho m by rho f into minus 1 times H actually here. Okay, so this is the expression that we get finally. Yes, so if you multiply with rho FG, then this is what you have. Okay, so this is the pressure difference actually. Now if this is the pressure difference, if you substitute here in this equation, if you substitute, let's see what happens. This piezometric differences can be written as rho manometric by rho fluid minus 1 into H is equal to V2 square minus V1 square by 2Z. So V2 square minus V1 square, A2 square by A1 square into V2 square, okay, is equal to 2G times, because this is 2Z into rho manometric by rho fluid minus 1, and this is actually a H here. Okay, so if you simplify this, if you take V2 square common, V2 square if you take common, then we have A1 square minus A2 square by A1 square. So A1 square minus A2 square by A1 square actually. So this is equal to, okay, so V2 square of this term is equal to 2GH or rho manometric by density of the fluid minus 1 times 2GH is what we have, correct? So that's 2GH times this. So V2 from this case is equal to A1 by root of A1 square minus A2 square into root 2GH times of density of mercury, whatever the manometric fluid, by fluid minus 1. Okay, so this is V2. So continuity, it gives you discharge is equal to area2 into velocity 2. So if you multiply A2, Q is equal to A1 A2 by root of A1 square minus A2 square times root 2GH times of this manometric by fluid minus 1. Yes, fine, we have this. Clear? So there is a square root for 2GH and this term also, which is actually this expression. Okay, it's simple to do, but actually it's a bit time taking, so that's why I thought of thinking actually. Clear? This is how you get the Venturi meter flow rate. Okay, similarly you can calculate for orifice meter or flow nozzle meter, anything in general. Is this clear to all of you? It's very simple phenomena. Basically you can apply this Bernoulli's equation, then to get this pressure relation you use manometry, then to get this discharge you use continuity. That's it. All these things if you put together you will get the equation, discharge. But actually what we have calculated is only theoretical. Okay, so theoretically this is what you have, but practically you have certain losses. So in actual case what you can say is this discharge is now normally called as Q theoretical, okay, TH, but Q actual is always given by some coefficient multiplied to Q theoretical, because this will be actually less. So this value is generally less than 1. Okay, so this is less than 1. So CD for Venturi is normally 11.92 to 0.96. 0.96 actually. Okay, so this is for Venturi meter in general. Okay, I think I have memorized the wrong formula. Sorry, it's okay. Yeah, cool. I understand. Fine. 0.96. Okay, so 0.96 actually. These decimals, you know, my handwriting is sometimes very pathetic now. 0.92 to 0.96. And normally if you see Venturi meter, Venturi losses in Venturi meter are low generally. Venturi losses in Venturi meter are low in general. Okay, so these losses are actually low. Now one more important point here is Q actual, CD, QT, H, and normally if you see the cost of Venturi meter, cost is also high, because manufacturing two nozzles at unequal cross sections and fitting them to a throat, welding and all, it's not very easy job. So normally it's take high cost to manufacture a Venturi meter. Okay, so these are the things that you can broadly speak about. Okay, Venturi meters. Fine. So this is how you can actually calculate theoretical. So normally if you give a pipeline, normally in case of a pipeline, let us suppose if I know if there is a pipe, if I want to calculate discharge, practically in labs and all, what we do is in general, you can understand this pipeline diameter is known to you, and once you know the Venturi meter, this A2 is also known to you. So in this formula, okay, in this formula, this A1 is known to you, A2 is known to you, this term completely is known to you. Okay, and you also know what is the manometric fluid you are using and what is the actual fluid flowing in the pipeline. So you also know this term. Okay, so practically what we'll do is we'll have some softwares and also some Excel sheets we can work out for a given pipe and Venturi meter combination. This is fixed, this bracketed term is fixed, 2Z is also constant. Okay, so we'll the input what we give for the calculations is generally 3 inputs. One is the manometric deflection, one is these two fluids, okay, densities. That's it. If you give these 3, then definitely you can calculate. If you standardize that always your fluid flowing in the pipe is water, and if the manometric fluid is mercury, then definitely this term is also locked. Just by knowing H, you can calculate these values. Okay, so if for fixed values of pipe Venturi meter, these fluids, Q is actually proportional to square root of H. Okay, so this is what you can understand in this case. Clear? Okay. Yes or no? Please type in the chat box. Is this clear to all of you? Of course, there are a lot of techniques to measure the discharges. Venturi is only one of the techniques, but again, very useful techniques. Okay, with very simple calculations, you can walk through different values. Okay, now let's see one last device before we step on to the next parts. RTT will just start in a moment. So if you see, we have this orifice meter. orifice meter. Okay, so in case of orifice meter, normally if you see, I'm explaining this because I want to explain you some physics here which is happening in the fluid. The main idea of this all meters, orifice, venturi, flow nozzle, is in the flow you should disturb the flow at some point to know about its discharge. Okay, so that's the main idea behind this. Now you can see orifice is very simple to construct in general. So let us suppose if we have a pipeline like this in which fluid is flowing. Okay, then the simple construction what we make here is we cut a plate, we keep a plate like this which actually creates certain orifice. Okay, this is an orifice plate in 3D, orifice plate which generally has certain hole, small hole actually, and basically this edge will be very sharp in general. Okay, so this is the orifice plate and flow actually happens in this direction effectively. Okay, now the main point here is this area is area of the orifice. If you take the streamlines for example, what happens here? The streamlines actually flow like this. You can understand practically what happens is, to slightly right there exists an area where cross section of the flow is minimum. Why the cross section of flow is minimum at this location rather than at this orifice plate is because, so can we call the cone angle? 12 to 15 degrees I have told you, no? Normally for higher side. Okay, can we calculate the cone angle? Simple here, just take a what do you say, this protractor and you can calculate. That's it. It's a physical measurement. That's it. Okay, clear? You can easily always calculate angles and geometrical anything that you can calculate very easily. Okay, if the calculation is complicated, you can use bit of trigonometry like we have used in hydrostatic forces and you can calculate. Okay, now see here, this cross section of the flow is minimum. Why the cross section of the flow is minimum here means somewhere after this orifice plate, but not at orifice plate, is because whenever the fluid is flowing like this, for example if you take this as a streamline, this streamline when it enters this region, it understands that there is a restriction in the cross section and it starts bending. Okay, so when it starts bending, because of the inertia, it tries to bend for small duration after this orifice plate. Understood? Means immediately after the, look, for example if this is the gap, the streamline cannot enter like this, no, immediately it cannot increase the flow actually. Okay, so it takes certain time, or it takes certain forward distance in order to get back to its original position to understand that the flow, like how it is understanding here, it's not understanding the presence of orifice plate here. Okay, it understands somewhere before because this fluid has experienced this. Similarly, because of this effect, it takes certain time for the fluid to understand the restriction has gone now and we can expand. Okay, so this is what happens. Streamline bending is not very instantaneous. Okay, it takes certain period of time, and clearly you will actually get a cross section less than this A0 after some time, which is slightly away, or at some distance which is slightly away from this orifice plate actually. Okay, now anyway, this area is called vena contracta, which you call this area AC generally, and the ratio of these two we call coefficient of contraction. Coefficient of contraction, which is generally this CC, is equal to vena contracta area by orifice plate area. Okay, means area of the flow at this particular location. Now you can actually connect the venturimeter again. So you connect this venturimeter at some points here maybe, and means in the uniform direction, and also here also where the flow gets stabilized. Okay, and dependingly you will have certain pressure difference like this. Okay, so this is the manometric fluid that you have in general, and this is the flowing fluid density rho f. Now one important point is accuracy in case of orifice meter is very less. Okay, practically if you see the coefficient of discharge, means Q theoretical, again you have some formula, is equal to, or Q actual is equal to Q theoretical multiplied with CD, coefficient of discharge. Okay, this CD value will only be somewhere around 0.68, 0.62 to 0.68 is what generally we say, 0.6 5 to 0.68. Typical range is this in actual cases. Okay, but anyway, in this kind of questions, they'll give you the CD if they want you to calculate actual discharges. But the technique for calculating Q theoretically is same. You keep this A naught, all these things. But main thing here is one thing that you have to understand: why these meters are why CD value is low, means why actual discharge is low compared to benchometer. Why actual discharge is low? The reason for this is, in case of benchometer, you have a smooth nozzle which actually guides the flow, correct? But here, in case of orifice, you have very sharp edges. The losses in the fluid will be generally large in case of orifice meter. And also, in venturi, the fluid has sufficient length or sufficient convection to understand that there is a converging and also diverging passages. But here, the effect is slightly narrow as compared to the venturi meter. Okay, so because of all these reasons, the discharge is actually less in this case. Okay, and also accuracy is low because in general, fixing this end of the manometer is very fine. You can actually fix it at some distance far from this, orifice plate, okay, to have the uniform flow. But here, identifying this location is not very, accurately done. Okay, normally we do this. We locate this location by using tail and error method. Okay, so how do we actually locate this? Practically, orifice plate, right? Normally you have an opening at some particular location of the pipe. You fix the orifice plate at that location and you flange it again, like how you do for a venchometer. Okay, when you fix this plate here, we start measuring pressures at different locations. Okay, like for example, I'll show you here. Let us suppose if the orifice is like this. One thing that you can get is, let us suppose if the actual vena contacta is here. Okay, but it's practically difficult for us to exactly identify this location. The reason is, how do we identify this location is because of by trial and error method is what we do. Trial and error method. Now, how we actually observe this is the vena contacta is, tell me one thing, at vena contacta flow area is minimum. If flow area is minimum, what about velocity? In the complete configuration, this flow area for the fluid is minimum at this particular location. If flow area is minimum, what happens to the velocity? Continuity again. It is maximum, correct? So velocity is maximum. Now, as per Bernoulli's equation, this is a horizontal pipe, for example. If velocity is maximum, what should happen to the pressure actually? What should happen to pressure in this case? Can we use this device at bending of pipes? Yeah, you can use generally. Yeah, we can generally use at bends also, but we should give sufficient, clearance, okay, to neglect the bend effect again. Okay, it's not exactly at the bend you connect, but somewhere just upstream of the bend and downstream of the bend you can connect. Okay, so if velocity is maximum, then definitely pressure is minimum. So what you do is, physically, you will fit pressure gauges. You fit a pressure gauge here and check the reading. Let us suppose if this is P1, let us say some 32 kilopascals, for example. Okay, then you keep here, this is 29 kilopascals. Let us suppose here you calculate the pressure is 25 or 25 kilopascals. Then again, when you come to this location, the pressure will increase. P is equal to 28 kilopascals. Let us suppose if this is the pressure. So when you actually fit the, let us suppose if this is my pipeline, okay, and if I keep fitting the pressure gauges here, 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 and on, if I keep on checking the readings, I'll definitely spot for the location where the pressure is low, and I'll assume that that location is the vena contacta, and I'll fit a manometer edge here. But fitting this pressure gauges need not be very accurate. The reason is, look, between here and here, when you have checked very closely, you have got 28 and 25, and slightly close here you got 29. So you decided this point is the minimum, and you declared that this is the location of vena contacta. But if you go in a minor scale, if you change, instead of changing by 1 centimeter length, if you change only by 0.5 centimeter for the location of the pressure gauge, between these 2 points you might get 24.8 kilopascals. Yes or no? This can also happen. So locating the pressure gauge, or locating the, basically the identifying the position of vena contacta is not very simple, and it's done on trial and error basis actually. So that's why we actually have very less accuracy in case of orifice meter because of these logics. Understood? Clear? Yes or no? Right? Did you understand why this is low? Because of this trial and error business. Okay. Fine. Anyway, you please take the formulas from here. Okay, so Q actual and Q theoretical you might have seen in previous cases, like the same how we have done for the venture emitter, same here, but using this CC we will actually adjust this area of cross section. See, practically what you will do is, look, whenever you apply Bernoulli, okay, let me spend some time. P1 by OZ, let us suppose if this is section 1 and this vena contracta is section 2, for example. Okay, so this is section 2. Now if you simplify this, P1 by OZ plus V1 square by 2Z plus Z1 is equal to P2 by OZ plus V2 square plus Z2 actually. Okay, so pipe is horizontal, you neglect this potential, guys. Then what happens here, let us call this distance like from here to here, you call this distance x. Okay, so if you do that, we can see P1 plus O fluid Gx plus O fluid Gh is equal to P2 plus O fluid Gx plus O manometric fluid Gh is what you have. Then this term and this term gets cancelled. P1 minus P2 by rho fluid times G is equal to O manometric by rho fluid times H. Correct? This is what you have. Yes or no? So P1 minus P2 by P1 minus P2 by OZ is equal to rho F minus is there, so minus 1 will also be there here, times H is what you have here. Correct? So this is what you get actually. Now if you supply this in Bernoulli's equation, let us see what you get. P1 minus P2 by rho Z is equal to V2 square minus V1 square by 2Z into, okay, so this is the equation. Then this equation can be replaced with H times of manometric by density of the fluid minus 1. Now how to identify this V1 and V2? The connection between them is V2 is actually the location of vena contracta. Correct? Vena contracta. But practically you cannot measure vena contracta area because that's actually the location where physically flow assumes minimum. So what we do is we use this guy to connect this and also this, because here you know what is the flow area, whatever is the opening area of the nozzle, whatever is the opening area of the orifice plate, same will be the area of cross section here. So what we can do is we can say A0 into velocity at orifice is equal to A2 into V2, which is actually the vena contracta. So we can write this as area at the vena contracta, velocity at the vena contracta. Okay, so VC can be written as, which is V2 of course, this can be written as A0 by AC times V0 actually. Okay, so this actually gives you A0 V0 is AC VC, and again from continuity you have A1 V1 is equal to A0 V0. So this A0 V0 can be replaced with A1 V1. Okay, so if you adjust A1 by A0 all these things, because AC practically you cannot calculate, so what we'll do one thing, VC velocity at the second location is equal to A0 by AC is what we have into you can actually do one thing directly. If you apply continuity between locations 1 and 2, what we can do, A1 V1 is equal to AC VC. So VC is equal to A1 by AC into V1. So this don't know directly, so we can reduce this as A0 by AC into V1. So this here is actually 1 by CC. So 1 by CC into A1 by A0 times V1. You know A1, you know A0, so you can calculate V1, only one unknown. Okay, we have converted VC in terms of V1. So if you put these two in this equation, you can get the velocity and correspondingly mass flow rate, or what do you say, discharge. Okay, so at vena contracta flow will be uniform, we assume that. Okay, actually it's not uniform because of just experiencing the effects of the nozzle and losses, but we assume that it's uniform throughout. Okay, in actual case at every location, like for example, even if you see this case, what happens, even at this cross section flow is not uniform in actual case. Okay, because there is viscosity, and normally when we solve Navier-Stokes we'll see we have a parabolic velocity profile. Okay, but here we assume whenever we are writing only we are talking about average velocity. Okay, discharge by area average. Clear to all of you? Okay, so this is what you get in this case. So just bit of manipulations could actually give you the result. Similarly, if you talk about pitot tube, okay, pitot tube, this uses the concept of stagnation points. Stagnation point. So what is this stagnation point? Is stagnation, you know this word, stagnated. Let us suppose some water is being present for a long time, we say the what is stagnated here. Okay, means basically it's stopped, it's located here. So cavitation chance can be created or not. Actually when we are very good question. Okay, so you want to know about cavitation. See, you all know what is cavitation? You all know what is cavitation actually? In thermodynamics you might have seen or not? It's okay, you might have not seen. Yes, you all know cavitation, right? So what happens is, you know, temperature and pressure are connected for any system. Okay, like for example, if I ask you what is, yeah, you know that. Okay, so normally if you see boiling point formation of bubbles, it's not air bubbles, actually the fluid molecules will actually get vaporized actually. Okay, we'll see what happens. Normally, you know, boiling point and pressure are very connected to each other from your basic thermodynamics. In your properties of your substances, I think Shivam sir might have told you. So this like the pressure and also the boiling point temperature and the pressure are very much connected, and you can understand as pressure decreases, the boiling point also decreases. Okay, so what happens is, corresponding to atmospheric temperature, there exists one particular saturation pressure. Yes or no? So whenever the fluid passes through the pipeline or maybe siphons, normally in siphons this cavitation issue is very highly preserved, in pumps all these issues. Now what happens when fluid passes over certain pipeline or siphon or any device in general, there could be certain pressure changes of the fluid, like how in case of orifice and venturimeters, fluid is undergoing some pressure change, so the fluid can actually go under pressure. When there is a process in which pressure is decreasing, if there comes a limit where the pressure achieved by the fluid is same as the saturation pressure corresponding to the atmospheric temperature, then definitely what happens, fluid starts generating bubbles. Okay, and these bubbles are very dangerous, they actually block the complete flow. Okay, so that's why when we are designing any devices, the main thing that we should take care is, first of all, whenever there is any process involving pressure drop, you should check for the pressure difference at any, normally when you're doing simulation or when you're doing the design, you should check for the pressure, and you should make sure nowhere the pressure is small enough to touch the saturation pressure actually. Okay, so you mean when pressure goes on below atmospheric pressure? Yeah, normally at atmospheric pressure, liquid water remains as, normally if you take water remains as liquid. Okay, but when pressure falls below atmospheric pressure in the pipeline, normally you see in condensers what happen, in condenser, normally if you have seen the power plants, when pressure gets above atmospheric pressure, it don't happen generally. Okay, now if you talk about water, look, for every fluid what happens, for every fluid, saturation pressure is function of saturation temperature, or you can say saturation temperature is function of saturation pressure. Basically these two are interconnected. So for water, example, for water, you know, this is somewhere around, you know, I don't remember the exact value again, you know, at atmosphere, one atmosphere at T sat T atm or at 30 degrees Celsius, we'll see normally we have this P sat is equal to something around 4.3 kilopascal something, I guess. Okay, so anyway, this value I'm not pretty much sure, we have to take from the steam tables. From the steam tables we'll take, so normally if you are operating pipe at atmospheric conditions, normally if all your pipes are going at atmospheric conditions, then we should take care that at this atmospheric conditions, whatever is the pressure that you can read from the steam tables, nowhere in your equipment the pressure should fall below this value, or it should touch this value in general. Okay, like let us suppose if, for example, let us suppose if this is 5 kilopascals, and if you are operating your pipelines and all at atmospheric conditions, you should make sure your pressure never goes below this value, or it should come close to this value, so that cavitation will occur. Okay, got it? Fine. Normally if you see condensers, the main issue with condensers is sometimes chances of cavitation are high because of air leaks and all, but again when you are designing condensers, normally this compressors word is coming in my mind, condensers will actually operate at a pressure below atmospheric pressure. Okay, so normally the reason for that is from second law and all, you will see normally I think ATD Vinod sir will go over this. Why you actually need a condenser is, if you don't have a condenser, the outlet from the turbine will be at very high temperature. Okay, so as per second law efficiency, heat rejection temperature will increase and thermal efficiency in the second law will decrease actually. Okay, so that's why we actually maintain a condenser. Condensers, if you see the operating pressures, normally 30 kilopascals, 40 kilopascals, in this range. Okay, atmosphere is 100. Okay, inside it's 30 or 40, that's it. Okay, so that's why condensers generally operate at a low temperatures in general, low pressures of course. Okay, low saturation pressures. Fine. Anyway, so we'll go to this concept of stagnation point. So what is the stagnation point physically is, the point in the flow or the location. Basically point means physically there is some location, so the point in the flow where the local velocity of the fluid is rest, is 0. The properties, we'll talk more about the stagnation properties, stagnation stuff when we talk about compressible flows. Maybe last but one lecture we'll talk about compressible flows actually. So we will talk about compressible flows in this case. Okay, so is 0, where the localized fluid velocity is actually 0. Now how this technique is useful for us in calculating velocities is, let us suppose you have a flow, for example. Now let's see, here it is P ATM, and here whenever you keep a pipeline or whenever you keep a small pitot tube, you know, we have already seen the, it's like a piezometric construction. So this is actually a pitot tube. Okay, now what happens initially, depending upon the pressure in the flow, the fluid will go and settle up to a certain extent, yes or no? So up to certain height the fluid will go and settle, if this is the case, for example. Okay, so the fluid will actually go and settle. Sorry, stagnation point have velocity is 0, correct, yeah, basically where the local velocity is 0. Now what happens when you keep a flow like this, definitely for this fluid particles this is a restriction in the flow. Okay, and this point, if you observe slightly close to this here, since this fluid is already in the, because based on the pressure this fluid has already entered here, so what happens when the flow, let us suppose if some streamlines are trying to come here but still there is no provision to go, so these streamlines will get deflected. Okay, so clearly there comes a location where you have a stagnation point. We'll see generally more about stagnation properties in compressible flows and stagnation points in potential flows. Okay, so stagnation points, this is stagnation point. Now what you can do is, you can apply Bernoulli's equation at these 2 points, then clearly you will understand that velocity is equal to square root of 2gh times this fluid by fluid by, normally if you generally connect a manometer also it can work out. So just a minute, let us do this thing, we can get this. So P1 by OZ, let us suppose if this point is 1 and 2, so P1 by OZ plus V1 square by 2Z plus Z1 is equal to P2 by OZ plus V2 square by 2Z plus Z2 actually. Okay, then you can see the pressure, if this is open to atmosphere for example, means for example you can see this is actually in the horizontal plane. Okay, we are not taking this in the vertical plane. So what will happen when I'll take water rather than mercury, where in this, whatever the fluid you take, okay, any fluid when you keep a restriction it experiences this point. Clear? Now in this case you can see, let us suppose you are doing this experimentation in a horizontal plane. For example, if there is some fluid flow, you have kept a pitot tube. Okay, you have kept a pitot tube. Then here P1 is P ATM, fluid flows in a horizontal plane. Okay, fluid flowing in horizontal plane actually. So in that case what you can do, this, whenever the fluid is flowing in the horizontal plane, let us suppose if there is some flow like this, and if you keep a pitot tube here, then depending on the pressure and velocity, this pitot tube will actually see certain rise of the fluid. Okay, normally in aeroplanes this is measured. Okay, to pitot tube in a plane, you can see normally below the pilot's cockpit it will be there, pitot tube in aeroplane. Okay, in aircraft you can see some images maybe, yeah, normally below the cockpit it is present. Yeah, you can see here this is the driver's cabin cockpit, and here you can see this is the pitot tube. Okay, this is the pitot tube here, small pitot tube will be there which actually can measure the flow velocities. Clear? For maximum velocity, stagnation point will take, no, actually if you see, when you bring the fluid locally to 0, locally, if means adiabatically, if you bring a fluid particle to rest, then whatever the properties that particle possesses is called isentropic, or basically this stagnation properties, and that local point where the velocity is 0 is called the stagnation point. Okay, so this is actually the pitot tube here. Okay, so you can see a lot of pitot tubes are there, so which can actually measure. So whenever A is flowing like this, then normally when A is flowing in this horizontal direction, this pitot tube will actually capture, and depending on the pressure exerted inside, this will give a reading corresponding to velocity. Okay, so if you do this velocity analysis, you can see this V2 velocity at this point is 0, then P1 is a P ATM, and this is P ATM plus rho GH is what, because you can see at this location pressure is actually due to this complete velocity gets converted to pressure head, and let us suppose if you don't have any data, sorry, this, then you can, by making certain simplifications, you can calculate what is the velocity in this pitot tube actually. Clear? Okay. So for expressions and all, we can upload notes. Again, like this is what you can do because time is running up slightly. So like how we have done the continuity and all Bernoullis here, same thing if you do, you can get the actual velocity expression for the pitot tube. And sometimes this velocity can also be measured using a manometers, for which you'll get out 2gh times like this calculation. Okay. So till this part, till this, where is this? Yeah, somewhere here. Till this part, if you do, you will get the velocity in terms of manometric and also fluid -1. We assume stagnation properties in pipe for maximum velocity. Sorry, you didn't get this. आप question हिंदी में पूछ लीजिए. I can understand Hindi well. Okay. Stagnation depends on water direction or not. I mean the relative velocity. It depends. Okay. It do depends. Fine. Okay. So let's see this. All things we can. This is normally for velocity measurement. Velocity measurement in this case. Okay. So these are certain flow measuring devices and all. And also you can see losses in pipes and all. We'll see. Normally if you apply momentum equation, okay, you will see minor losses in pipes. Minor losses in pipes actually. Okay. So this is minor losses in pipes. Now when there is a sudden expansion, then what happens here is the streamlines will take this direction, and if you take this control volume, and if you apply linear momentum equation, and Bernoullis, okay, you will find out the loss due to sudden expansion, HL, sudden expansion will be equal to V1 minus V2 whole square by 2z. Right now I'm not doing the derivation. Normally in detailed courses we do the derivations, but right now we are not doing any derivation for this. Okay, it's very simple. Normally you have to apply this pressure P1, A1. This area is A1. Okay, and this is P2. This area is A2. Okay, and you will see the pressure here will be same as this pressure at this location P1 because of sudden expansions and also experimentation. Here there is some small concept called flow reversal which will generally stop. Okay, so flow reversal can happen. We'll study about these things maybe in some Mahayojana or somewhere in the future. So before the exam. Okay, so flow reversals, we'll see what is this concepts and all, but right now we are just focusing on equation stuff. So we have V1 minus V2 whole square by 2z. Okay, so if you take this V1 out constant, V2 square. Okay, so let us suppose if we have, for example, V1 minus V2 whole square by 2z. So if you take V1 common, V1 square by 2z into 1 minus V2 by V1 whole square actually. Okay, now whenever there is certain entry, okay, so let us suppose there is a large or let us suppose if there is some entry which is taking place into a very large chamber. Okay, so this is a very large chamber, so this is A1 and this is A2, a very large tank. For example, the fluid is getting entry into this point, okay, or exit, you can say this. This is entry. No, yes, normally it is entry into the tank. Then from continuity equation, if you apply A1 V1 is equal to A2 V2, then V2 by V1 is equal to A1 by A2 in general. Okay, now whenever A2 is very large, it's like a tank for which the fluid is coming through a small pipe. Can anyone tell me what is this value of A2 by A1 or A1 by A2? This value will go to which value? Yeah, please tell me. A1 by A2. If A2 is very large, let us suppose if a small pipe is discharging the fluid into a large tank, then what about this A2 by or A1 by A2? Zero, right? Yeah, it tends to 0. So this value is tending to 0. So if this value tends to 0, this value tends to 0. So this NT loss is actually V1 square by 2z. Normally if the pipe is actually having certain diameter, so average velocity of the pipe in this case by 2z is what we have. Continuity equation versus 3D continuity equation, nothing difference. Okay, it's just the number of dimensions we take. Okay, we'll see in Navier-Stokes equation, we will see. Okay, we generally take the 3D case and we will keep certain terms zeros in them. Okay, so this is what you have, a1 by a2 is equal to 0. Similarly for NT, similarly for exit loss and also contraction losses, sudden contraction, you have the formulas which you see 0.5 v2 square by 2z and things like that. Okay, 1 by cc minus 1 whole square v2 square by 2z, you might have seen these things, right? This 1 by cc, coefficient of contraction minus 1 whole square is like 0.5. We'll see all this stuff. Fine. So with that, we'll quickly jump into RTT. Okay. So is this clear to all of you till this point? Flow measuring devices, this pitot tubes, then after this losses, whatever we have discussed. Is all these things clear? Fine. Everyone. So please type in the chat box. Is everything clear to you till this point? If things are clear, we'll go to Reynolds transport theorem. Okay. Clear? Then, yeah. Fine. So let's get into some basic stuff again. So normally, control volume. A region in space which is under study. Okay. A region in space which is under study. Which is under study actually. Okay. So which is under study. Sorry. This study. Okay. So now let's get into certain understandings. Normally when you try to calculate any forces acting on bends and all these things, general expressions that you see in books, and also I have seen few people explaining this. For example, let us suppose there is a wall. Let us suppose some fluid is going and hitting this. Okay. And this guy is fixed. For simplicity, let us say this is fixed. Okay. Now, what you generally understand is they'll say F is equal to ma, and they'll write the momentum equation m into dv by dt, and they'll tell you m dot this dt by m gives you m dot, and change in velocity, so v out minus v in is what they tell you. Correct? Yes or no? This is what you have seen. So f m out v out minus v in is what you have seen. You'll put v out v in, you'll get the force expression. Yes? This is how you actually calculate. Correct? Yes or no? Correct? Huh. In this, the answers will come correct, unfortunately, or fortunately, let us say, the answers come correctly, because you're actually doing two mistakes, and if you do these two mistakes simultaneously, you'll get correct answers. Okay? It's not like you should do only one, you should do both the mistakes simultaneously, then you'll get this correct answer. Okay? Conceptually, there are two mistakes in this, but if you do these two simultaneously at a time, you'll end up with correct answers. Okay? What are the two mistakes conceptually is, this expression is for a particle or body, first of all, which has fixed mass. Understood? Fixed mass. But in fluids, or whenever there happen certain flows, what happens here is, if you for example choose any control volume, this is the case only this mass within this control volume, means if you take this control volume, this mass is fixed only if it undergoes in steady state. Okay, point number one. Point number two, this force acting on the fluid and this acceleration are on the same body. Yes or no? Correct? Like for example, let us say, if for example I have let us suppose I have my phone. Okay, for example, let us say I have my mobile here. If I have a mobile, if I keep this mobile on my hand, if I apply force, for example, the body moves. I don't want to move much because it will fall down. So if I apply force, the body undergoes certain motion actually. If you see, force applied and acceleration are related to the same body. Yes or no? If force is applied on this body will accelerate. Correct? Now, tell me one thing. Whenever you are doing this, you will say F is force acting on plate. Correct? This is momentum change in fluid actually, which means momentum change in fluid. In other words, acceleration or the momentum change weight in the fluid actually. Then this is on plate, this is on fluid, but mathematically they are equal. Why? Did you understand? These two terms do not belong to the same body. Clear? This is the force acting on the plate is what you see, and this is the expressions for momentum change is what you write. Are these two related to the same body? Are these two related to the same body? You can understand. This is the force acting on the plate. This is the momentum change on the fluid. But how these two are equal? Because linear case. No, it's not about linear case. Newton's third law. If you go to Newton's third law, you will understand certain important things. Okay. So these are the two mistakes which you are doing simultaneously. If you do these two mistakes at a time, you will end up with correct answer. Okay. But anyway, we'll actually try to look into the basics of this control volume analysis, and we will get in touch with the things. Okay. But for that, first of all, I want to explain you some small things which are of importance. This is very important actually. Okay. So Newton's third law of motion. See here carefully. In Newton's third law of motion, generally what some of the schools teach you is, whenever there is a wall like this, then let us suppose this is me. Let me have some spikes also. I'll look good. Fine. Okay. Now let us suppose with this hand I am throwing a ball onto the wall, for example. Okay. Now when I am throwing this ball onto the wall, people tell you this is action and this is reaction. Correct? Yes or no? Like they'll tell you, if you throw a ball onto the wall, you will get it back. So if going off the ball is the action, then getting back is the reaction. So similarly, this is Newton's third law, is what they'll tell you. Right? How many of you have heard this? Acha, equal. Okay. Ball travels by same distance. Okay, equal. How many of you learned the Newton's third law in this way? Because I want to make your concepts clear, because RTT is one really fantastic application using which majority of the fluid mechanics problems you can simplify to a great extent. Okay. But actually, this is not the Newton's third law. Understood? If you throw stone, it won't come back. Exactly. If I throw my mobile, will it come back? If I throw this marker, will it come back? If I throw my water bottle, will my water bottle come back? No. Obviously, they won't come out, or they won't come back. Okay. Now the reason why they don't come back is, Newton never mentioned about elastic bodies, perfectly rigid bodies, nothing. Okay. So Newton never told. Newton's law is perfectly valid, but we understood it in a different way actually. Newton's law is not this moving of the ball and coming back of the ball. Okay. So this is not Newton's third law actually. Newton's third law is valid when bodies are in contact. When bodies are in contact. Okay. Like for example, let us suppose if I want to break this phone, for example. Okay. If I want to break this phone, definitely I have to apply some force on this. Without applying any force, if I just see the phone like this, just folding my hands and just watching at the phone, will it break by itself? It won't. Correct? Now, but when I throw it onto the wall, definitely it will break. The reason is, actual Newton's third law of motion tells you every action force. I have never seen this word in any of the textbooks that I have seen in school. Every action force has an equal and opposite reaction force. Opposite reaction force actually here. Okay. Now let us see, has every action as an equal and also opposite reaction force. Now whenever this ball and wall are in contact with each other, when this applies a force F on this, this will also apply a force F exactly in the linear but in opposite direction. Okay. Yes, every action force has an equal and opposite reaction force. That's why when the ball is traveling, if you, like for example, let us suppose if you throw a phone. Okay. For example, if you throw a phone, if action starts here, if action force starts here, the phone should start breaking here. Yes or no? But it won't break, because till this phone becomes in contact with the wall, there is no reaction force which is exerted, and as you travel here, phone doesn't break here, doesn't break here, doesn't break here, but when it gets in contact, it gets break because there is a reaction force which is applied on the phone actually. Okay, so anyway, when you are writing these formulas, when you have a wall, you have a fluid jet, all these things, the actual thing what you're writing is force exerted on fluid or on plate, force exerted on plate is equal to minus of force exerted on fluid, and this force exerted on fluid from Reynolds transport theorem we will see this is actually a material, and we are interested to write the control volume. For example, if this is your control volume, the momentum change of the fluid in this control volume and the momentum changes or basically any property change of the material and the control volume is related by this Reynolds transport theorem. Okay, we'll see what happens here. Okay, so this whatever the expressions we write, momentum change, net difference between inlets and outlets, we'll see how this is coming and all. So but this practically what Reynolds transport theorem do to you is it actually connects your property change, because this momentum change in the fluid is because something is changing inside this control volume. Okay, so inside this control volume we have material, and whenever the properties of the material change because of some effect taking place, like here for example it is getting diverted. Okay, so it is happening because of certain physics happening. So the material change, the material is inside the control volume, and the material change which is inside the control volume is related to the change of property of this control volume using this Reynolds transport theorem. Okay, so see, we'll go in detail. If you see the Reynolds transport theorem, Reynolds transport theorem, normally this transport phenomena are very important in fluid mechanics and heat transfer. Okay, which we will maybe in this gate examination level we may not see this, but when you go to advanced studies it's highly appreciable. Okay, so Reynolds transport theorem, so you can understand it connects rate of change of property, for example say B, of any material to the rate of change of property of control volume rate of change of control volume in which the material is located, or crossing. Sometimes during flow material will actually cross. Okay, crossing. Like let us suppose you have a control volume at a particular time t. I'll just try to give you an example. This is a control volume V. At time t, let us suppose these are the particles which are present inside. Okay, so these are the particles which are present inside. Okay, these are the particles which are present inside. Now at time t plus dt, what happens? T plus dt, these particles which are here will get displaced here. Yes or no? This is actually control volume, means whatever the volume you take, control volume at t and t plus dt, whatever the time you take, the volume remains there. Let us suppose if it's a tank remains there, but fluid inside the tank will actually fluid will actually cross the boundaries of the tank, it flows outside. Okay, this control volume at time t is also coinciding with system at a time t, but this configuration is actually system, means all these particles will move to some new configuration at time t plus dt whenever you have a flow actually. Okay, now because of this moment, so where is your heat and mass transfer playlist? I never taught on YouTube. Okay, yeah, so anyway you can see here this is system at t plus dt. Okay, so whenever this is at system at t plus dt, then because of this flow of the system, this control volume will have certain change in the properties. Yes or no? Because what, it's not mandatory that let us suppose if the particles leaving has certain temperature and they have certain enthalpy, it's not mandatory that the new particles which are coming inside will have the same temperature and same enthalpy and same kinetic energy, whatever. Correct? Can you understand clearly? In this case of control volume, when these particles are moving out, definitely there could be the change in properties of the control volume, because the new particles which are entering may not have the same energy levels or same kinetic, same potential, whatever, compared to these particles which are leaving the system. Yes or no? So there comes certain change in this properties of the control volume. So therefore that properties change in the control volume is connected to the property change of this material using this Reynolds transport theorem. Got it? And normally in the first lecture I have asked you to see yesterday. Did anyone see that? First lecture of control or second lecture of control volume analysis. Have you ever seen? Did someone see this? Control volume analysis. Second lecture I asked you to see. I have derived Reynolds transport theorem in the second lectures. Okay. If someone missed in yesterday's class, I'll just show you. You go to YouTube. Okay. Then you type 𝐂𝐸 English. You type 𝐂𝐸 English, actually English, yeah, 𝐂𝐸 English. Then here you can see this is potential flows. I have taught in complex numbers, of course, but yeah, if you go to videos, then you can find, yeah, these are the videos. So this video, control volume analysis of fluid systems 2, in which I have derived the Reynolds transport theorem. You can go for that. Okay, so if you go there, we define a property called B. For example, B is property of the system. For a property B of the system, for what is the time, by the way? We are teaching some nice concepts, but 8:45. Okay. So control volume की can't condition होता है, मतलब it's basically volume. Okay, that's it. It's just a volume. Fine. Now let us see. So for any property B, we see. Okay, let me write here in the next page. If you have a control volume, if this is a control volume V, and if this is the control surface, definitely if it's a volume, it's bounded by some surface. Control surface. Okay, so this is control surface. Now if this is control surface, then we can understand one thing. For any property, let us suppose if B is the momentum or mass or angular momentum, anything which is going in. For any property B of the system is actually material, okay, of the system, your dB by dt of the system is equal to dou by dou t of time rate of change or the complete control volume beta times so dV. dV is actually some small volume which you pick here somewhere, maybe in the some location you pick some small elemental volume dV. Then this is the time rate of change plus integral over the control surface beta times rho VR, the relative velocity at which fluid leaves, times n cap dA. Okay, so this is, or ds, whatever you want you can say. So this is dA, the elemental surface, and this is the n cap, which is normal, outward normal to this dA actually here. Okay, n cap is actually outward unit normal to dA actually. Okay, this equation I have derived in that video, so please go through that video once. Okay, now if this is the case, try to understand one thing. This is net rate of change of property of system, this is net rate of change. I'll explain you these terms just a minute. Net rate of change of property of control volume, and this is net rate of flux, net rate of a flux crossing the control surface. Okay, so crossing the control surface actually, crossing the control surface. Look, can anyone tell me, if B is the complete property and if I define beta as B per unit mass, this is intensive, this is extensive, that's it, okay, in general. So beta is actually capital B divided by mass. Okay, then if I want to calculate this term, actually gives me the small change of B in this volume. Yes or no? Correct? Look, this is density into volume. So density into volume gives you d mass. Yes or no? Density into volume gives you small elemental mass. So if you multiply small elemental mass with this beta, you will get the small change in the property capital B. Correct? Because this beta is per unit mass. So if you multiply beta with unit, some small amount of mass, say dm for example, because density into volume gives dm. So this dm into beta gives you a small change in the property beta actually. Okay, so if you get a small change of property beta, then what you have to do to calculate the complete change in the control volume, you have to integrate it over the complete control volume. Yes, and the time rate of change of this quantity is nothing but dou by dt. Is this term clear to all of you? Is this term clear? This is actually a scalar rho dv. So this is dm. dm times this beta gives you this. Clear? So this term actually defines the change of capital B in the control volume actually. Okay. How these terms are coming, please go to that video, but right now understand the terms. Actually, this is the property change of the mass which is actually present in the control volume, or which is your system of interest. This is the total property change in the control volume, and this is basically, you can see this rho v dot n cap dA. This is actually nothing but mass flow rate. Yes or no? So this is m dot again. So this m dot multiplied with beta gives you the rate of property which is entering. Okay, we'll see examples. We'll apply it for mass, momentum, I mean linear and angular momentums. You can understand it better. Okay, so this is m dot actually here. So if that's m dot, this, because you know continuity, rho vr dot bar and dA. Last class I was telling you, when I'm talking about continuity equation, I have taken a pipe. I have taken v average dot dA bar, v average dot n cap dA, all these things. Okay, you said beta is constant, then dv is also can also be constant. I'll tell you. Okay, just give me some minute. I'll convey you why dv is actually constant here in this case. Okay, so this is m dot. This dv is constant. Of course, we have chosen a particular fixed amount of dv. Okay, now this is m dot. So this again gives you the net effect of property which is crossing this control surface. Clear? Look, I'm telling the property change of this control volume is nothing but, or this system which is lying here is nothing but property change in this control volume plus whatever is the net effect which is coming inside. Look, for energy, like for example, for energy, you know, energy change of the system is nothing but energy change in the control volume plus this energy which is actually flowing inside. That's what, for any property. Okay, I'll make you understand to the examples, you can understand it clear. See, for example, if you apply the equation for mass, let B is equal to m, means you want to calculate rate of change of mass of the system. Okay, so rate of change of mass of the system. If B is equal to n, can anyone tell me what is beta? Can anyone tell me what is beta? We'll see through the examples, linear momentum, angular momentum, and also we'll apply for continuity for mass actually, we'll see. So can anyone tell me what is this beta in that case? What is mass divided by mass? Beta is capital B per unit mass, correct? So beta is actually 1. Okay, system is actually identified by set of particles. You know, system is actually some fixed amount of mass what we are taking. So this is identified by some set of particles actually. What are here? Okay, now when they are identified by some set of particles, if you apply this conservation equation, dB by dt of the system is equal to dou by dou t of integral over the control volume beta times rho dV plus integral over the control surface beta times rho vr bar dot n cap dA is the equation. Okay, now can anyone tell me, if you are taking system as some particular mass actually, so mass is actually identified by some particular particles, yes or no? Let us suppose if I take this is my mass, then this mass has certain, for example, this mass is actually identified by some particles actually. So can anyone tell me, if I take some mass, what happens to time with, what happens to mass with this time? Means for example, if I take this mass as m here, if I take this mass as m, this beta as 1, this beta is also 1. If I take this, then can anyone tell me what is the value of this term? mass is always fixed, correct? It is always taken by identity of some particles. Like for example, you see in this control volume, when I say mass is flowing, what this location of the particles, or basically these particles are nothing but the initial particles which are present in this control volume at time t, correct? This mass is actually fixed. Whatever the location of the particles or whatever the particles you identified, your focus will be on that particular particles as long as you call system. Okay, so what is this dB by dt of this mass, or what is dm by dt? What, with respect to time, are you changing any of your particles that you are studying? Volume is fixed, okay, and also mass is fixed. So with respect to time, is there any change in this particles? No. So if there is no change in particles, clearly this term is 0. Okay, now come to one thing here. 0 is equal to dou by dou t of integral over the control volume rho dv is what we have, plus integral over the control surface. It is closed because you can see this having some volume, so this is closed. So closed times rho vr bar dot n cap dA actually. Okay, so this is dA because the control volumes can be sometimes moving. Okay, now for non-deformable body, for non-deformable bodies, like we have also seen for non-deformable, whenever you are taking continuity equation, we have taken a cube and we have told that this cube shape is not changing with time. Yes or no? You might have seen when we are talking about continuity equation, in a flow we have picked a small differential element, and in that differential element, what's happening here? In that differential element, whenever we are analyzing, flow is going from the left face, coming from the right face, all these things, during all these analysis, we assumed this control volume, whatever we have taken, the small elemental volume is not changing its shape with time. Yes or no? We have never brought the instant of time into the picture. Okay, so therefore for non-deformable bodies, this dv will not change with this time, so therefore this integration value will be same even if you shift this dt inside. This you can do only for this case, because if this is changing with time, you cannot take this integration out and put this differentiation inside. Okay, but for this case what you can do mathematically, since this effect is not changing with time, you can differentiate it with respect to this density changes, and also you can take this density out. So 0 is equal to integral over the control volume dou by dou t of rho dv, and since this is not changing with time, you can take this out. So rho into, because this dv is not changing with time, so this is dv. You have fixed some location of dv actually, plus now this is actually a closed surface. You know something called Gauss divergence theorem. In maths you might have studied this. I don't know whether you might have studied, but definitely yeah, you might have studied this still. If you see the Gauss divergence theorem, which is very powerful again in electronics, mechanical, everywhere. Okay, when you are dealing with electric fluxes, magnetic fluxes, fluid fluxes like this, we have, let us suppose if we have some volume V, and this is control surface S, for example. Now what you get is, let us suppose if there is some force or some vector which is acting at this location. Okay, some vector which is acting at this location v bar. It is some vector, it may be velocity or anything, and the normal to this is n cap, for example. Okay, to this small area, let us suppose that's n cap. So what we get is, when you evaluate the complete integral over the complete surface, v bar dot n cap dA. Okay, so whenever you do this volume integral, v bar dot n cap dA, v bar dot n is actually the component of this v perpendicular to this surface, means parallel to this n actually. When you do v dot n, n cap is actually unit vector. Like for example, if you do v dot n, by your definition, v n cos theta, where theta is the angle between these two. Okay, and n cap is having a magnitude of 1, so this is magnitude of v cos theta. So therefore v dot n gives you the component of velocity in this particular direction. Okay, so that if you integrate over, this gives you integral over the control volume, total volume integral, it's a table integral, divergence of v over complete dv actually. Okay, this is a scalar function because divergence of a vector is a scalar, and you can do a normal integration, table integration to calculate this value. Okay, but the thing is, this should be, v bar should be continuous at every point. It should be there. It can be 0 also at some points, but it should, there's nothing like at some point you cannot define velocity. Okay, what are the concepts for applied apply closed integration. This theorem is what basically it connects the surface integrals with the volume integrals, okay, and we take the help of this particular Gauss divergence theorem in order to compute this term, okay, in order to compute this term. Now this second term, if you apply the Gauss divergence theorem, what we can say, in a control volume, this surface integral can be converted to control volume, divergence of rho v bar into dv, correct? This is what you can write by Gauss divergence theorem. By Gauss divergence theorem is what you can write. Yes or no? This is by Gauss divergence theorem. Now both these integrals are of control volume on the same control volume, and this dv of choice is same, so we can write this as 0 is equal to integral over the control volume dou rho by dou t plus divergence of rho v r bar dv is equal to 0. Can I write this equation? Can I write that equation? Is that clear? This term of surface integral we have converted to volume using the divergence theorem, and this expression completely is equal to 0. Okay? Is this clear? We have taken the advantage of Gauss divergence theorem and we converted this surface integral to volume integral to get this equation. Okay? Now, main point here is, when we are defining this, did we make any specifications for choosing this dv? When we are doing this complete business, at any point did we put any restriction on this dv? Like, did we make any particular choice of dv in the control volume? Let us suppose if this is control volume, for example, then did we particularly make any choice for choosing the dv? No, we have not chosen, correct? Means this integral is 0 for any choice of the control volume. Okay, so therefore you can see wherever you choose this dv, this term is 0. That means clearly, since choice of dv is independent, choice of dv is independent, since choice of dv is independent, then clearly you can say dou rho by dou t plus divergence of rho vr. If control volume is static, you will just write this as 0. Okay, but anyway, the relative is the correct thing, so rho vr is actually 0 in this case, and that's nothing but your continuity equation. Okay, normally if you know this Gauss divergence theorem and RTT, 1, 2, 3 steps is what you'll see for getting your continuity equation. Okay, this is in the control volume analysis. Now all your expressions of force, like how force is equal to momentum change and all, I'll just tell you in a while. Okay, so is this clear? First of all, so please type in the chat box. When I say you linear momentum, things gets cleared. Okay, this is for the continuity equation, which you can see. Now let us look at linear momentum equation. If b is equal to momentum, okay, beta is equal to v, because if you divide this with mass, you will get beta is equal to velocity. Okay, in case of, in the expression of Gauss divergence theorem, dv is constant, like we considered in earlier terms. Yes, basically we change we choose dv, but that dv is actually time independent. Okay, that's what. Clear? Now let us see all understandings you will get here in this linear momentum. Conservation of linear momentum is what you can say. Linear momentum. Okay, so this is conservation of linear momentum, like how this is conservation of mass. You know, this is continuity equation actually. Then if you understand this linear momentum carefully, you will understand all the logics that are involved. Okay, so see carefully. As per Reynolds, RTT gives you dB by dt of the system of the mass is equal to dou by dou t of integral over the control volume beta times rho dv plus integral over the complete control surface beta times rho this v. Okay, let me take the control volume is fixed dot n cap dA. Okay, so this is for a fixed control volume. Okay, then you take your case of a plate, for example. Then if you take the plate, then definitely this is the volume in which the fluid is completely changing its velocity, and also this is the location where things are happening. Okay, so this is your control volume. The dotted, whatever I have dotted, that's the control volume, because the fluid is changing its momentum, the fluid is changing its properties in this region. Okay, because this is a solid plate. Okay, you know, this guy is a solid, there is no penetration, nothing. So let us suppose this is solid. Then fluid actually enters like this practically and it gets splitted. When fluid is splitting like this, the momentum or the velocities of the fluid are changing in this region. So we have chosen that region for our point of interest, and this is actually a control volume. Okay, and the fluid which is actually present here, this fluid which is actually present at that point is a system. Okay, is this clear? What n cap signifies? N cap is basically the outward unit normal. Okay, because when I'm talking about mass conservations, I have told you this area and velocity had to be perpendicular to calculate mass flow rate, correct? That's why we put an n cap. You remember when I'm teaching you mass flow rate, this formula rho AV, I told you this A and V should be perpendicular to each other using this n cap I think in the 2-3 lectures down the line. Okay, so that's what n cap signifies here. Okay, fine. So this is your control volume, this is your system, and the system is changing its nature in this region, so we have taken that as the control volume. Now if you apply this for B is equal to mv, d by dt of momentum of the fluid is equal to, for simplicity let us take steady state. Okay, so if you take steady state, then when you take steady state, what happens to this time derivative? Can anyone tell me what is this value if you take a steady state? This is a partial, it's not a total derivative, so it's a partial derivative. Okay, so dou by dou t, so rate of change of this thing with respect to time. So what is this value? 0. Okay, so this guy is 0. Then into the control surface you can see beta times rho v dot n cap dA. So to this control surface, let us see what's happening here. On the fluid is equal to integral over the control surface closed beta is actually v times rho v dot n cap dA. You can clearly understand this expression is actually elemental mass, correct? Mass flow rate rho AV. So that's actually a elemental mass flow rate actually. Okay, now this amount of mass is crossing this control surface at this velocity. That's what this term actually means. Understood? I'm repeating, this amount of mass per unit time is crossing this control surface at this velocity v. Crossing can be in two ways. Let us suppose if this is control volume, here it's crossing, here also at this is crossing here. Okay, so crossing can be due to entering of the fluids or also exit of the fluids, but whenever certain mass crosses particular control surface at some location, that effect is mentioned in this term. Is this clear to all of you till this point? Okay, is this clear to all of you till this particular point? This is using RTT, of course, because I'll ask you step by step, so please confirm me. Okay, if you have doubt at any point, you can talk to me. Okay, now this integration is when you have multiple inlet and multiple outlets of the control surface. Like for example, you have a control volume like this, and let us suppose if fluid is coming in, going out in different variations, at every point we do the integration. When you have some finite number of inputs and outputs, what you can do is, first of all, tell me one thing, this is nothing but a rate of change of momentum of the fluid, correct? So this is nothing but rate of change of momentum of the fluid. So what is rate of change of momentum of a particular mass of fluid? Can anyone tell me what is the rate of change of momentum of any mass? Nothing but force F, correct? So this is nothing but force acting on fluid is equal to force acting on fluid is equal to, now when you have some finite number of inputs and outputs, you can look, it depends on this n cap. I'll explain you some bit of maths again. See here, whenever, let us suppose if you have some surface like this, if you have velocity leaving like this, and through this small section dA, if your n cap outward normal is in this direction, and if the angle between these two is less than 90, then this v dot n cap, or basically this v dot n here, is positive. Yes or no? V dot n is positive, which means this V is also creating an effect in the outward direction. So basically mass actually leaves. When mass is coming inside, you can understand. Let us suppose if this is the surface, for example. If this is dA, your n cap is like this, but let us suppose fluid is entering in this case. Okay, so when fluid is entering, when fluid enters like this, V cap or V bar, for example. Okay, so this is V bar. Can anyone tell me V bar dot n cap, if you do this dot product, will you get a positive quantity or negative quantity? Will you get a positive quantity or negative quantity if this is the case, if fluid is entering here? N cap is always directed outward of the surface. Can anyone tell me? Can anyone please tell me what is this, positive or negative? It's negative, right? Because this angle between these two guys is more than 90. Yes or no? Velocity is coming like this, n cap is like this, so this angle is more than 90. Okay, so anyway, if you see, this is negative. If you understand this case here, this term, since you have some finite number of inputs on outputs, finite locations where fluid is actually crossing the control volume, you can understand this can be written as sigma. You can write this as m dot V at the outlet, means all the control points where the fluid is actually going out, plus, but you can understand one thing, at all the points where the fluid is actually coming inside, this dot product is going to be negative. So therefore we can write this as minus sum of all the momentums which are actually crossing in. So this is how this expression actually comes out in this case. Understood? And this is vector and this is also vector because it's a vector. Clear to all of you? Is this understandable to all? How I have written this from this equation? Because understanding the normal directions, if you split all these points into two categories, one set of points where fluid is actually going out and one set of points where fluid is actually coming in. So sum of all those points where fluid is going out will be positive because this dot product is going to be positive. And similarly here, this term, this minus sign will actually comes out because this dot product will be negative for all the locations where fluid is actually coming inside. So these are the velocities at which the fluid is actually crossing the control volume. Understood? Yes or no? Is this clear to all of you? Yes or no? Okay. Now the main thing here is, so this is the net force acting on the fluid by Newton's third law. Now before I give the final concluding step, I want to explain you one thing. All of you know that if you have a plate like this, if you have a plate like this, and let us suppose if this is the control volume actually, and if the fluid is leaving like this, and if this plate is fixed, for example, then you know if this is coming out with velocity v, if there is no friction, it leaves with velocity v like this, then force acting on plate is equal to rho a v square. If a is the area of the plate, a is the area of the jet actually. Okay, so a is the area of the jet. You know this, correct? You all know this formula. You all know this formula, right? Yes or no? Let us suppose if a fluid is going on impacting a jet, then the force exerted by the fluid on the plate is actually rho a v square. Now using this expression, I'll explain you how that's happening. Okay, and this is horizontal in the x direction. You know. Similarly, you'll calculate Fy is equal to 0. Okay, you know this. Let us see how these terms are coming. Basically using this equation. By Newton's third law, sigma F on fluid is nothing but, because the fluid, this body and this mass are in contact with each other, definitely there exists certain reaction. Correct? Things will be same but with a minus sign, negative of this vector. That's it. Okay. Now if you see sigma F acting on plate is equal to minus of sigma F on fluid, and sigma F on fluid is this. This means we can say sigma m dot v at the outlet minus sigma m dot v at the inlet. Okay, so this equation is in vector form. If you resolve it in x and y directions, we can say sigma fx on plate is equal to summation of m dot into x component of velocities at the inlet. This is in minus out, okay, because we have taken on plate, so minus of the momentum change of fluid. So this is in, this is out, correct, because this is actually out minus in. So if you put a minus, in minus out is what you'll have. Okay, so minus sigma m dot v x in the outlet direction. Now if you take this particular control volume, the fluid is actually crossing the control surface only at 3 locations. Yes or no? First location, second location, third location. These are the only 3 locations where it's crossing. So if this is v dot x in and v dot x out, sigma fx on plate is equal to, so first of all let us see the outlets. Okay, inlet. At inlet you have only one inlet, so there is only one term corresponding to this summation. In this summation you'll have number of inlets, and in this summation you'll have number of outlets. So here we have only one inlet. So if you see, what is the mass which is flowing at this point? M dot, which is equal to, m dot is equal to rho av, if this is a jet times velocity v. So at this first point at the inlet, this mass flow rate is rho a jet v jet into v inlet in the x direction. Okay, so x component of velocity in the v direction. For example, if you take this as your coordinate system, x and y, so x direction is actually v is what you have. Okay, so v jet, for example, you say v jet actually, so v jet is what you have, minus at the outlet, this fluid is crossing the control surface out at 2 locations. So small spelling error, plate in place of plane. Acha, sorry, thank you, this one, on plate. Okay, yeah, thank you. Now here, can anyone tell me, when it's crossing out, there are 2 locations where the fluid is actually crossing this control surface. At these 2 locations, is the fluid having any x component of velocity? If x is defined in this direction, at those 2 outlets, is there any fluid which is passing and having x component of velocity? No. So in this summation there is no term which survives. Okay, because at every location there are 2 locations actually where fluid goes out, but at both the locations this Vx is actually 0. So this is what you have. So force acting on plate is equal to rho a jet v jet square, which is this. Okay, similarly if you split this equation in y direction, let us see what happens. Sigma fy on plate is equal to this term. If you write again, sigma m dot v in the y direction minus sigma m dot v out in the y direction. Okay, so this is what you have. Now out of these 3 points where it's crossing, okay, first of all let us take the inlet points. Inlet, so in this term you can see there is inlet only at one point. At this inlet point, what is the y component of velocity? Because you want y component of velocity at the inlet locations, so there is only one surface which is going out. So what is the y component of velocity at here? 0, right? Y component of velocity is 0 at this inlet, so definitely this term will not survive. So this is equal to minus. Now let us suppose if the mass is splitting equally, it's generally it happens this way. If this is m dot, the mass which goes through this is m dot by 2, the mass which comes out through this is also m dot by 2 actually in this case. Okay, so m dot by 2 and also m dot by 2. Now try to understand, if you take this summation at the outlets, there are 2 outlets, outlet 2, so we can say m dot v out in the y direction at outlet 2 plus m dot v out y at this location at outlet 3. So if you simplify this, minus at location 2, the mass flow rate which is flowing out is nothing but m dot by 2, correct? Half of the mass flow rate is actually flowing through this, and that mass flow rate is flowing at a velocity. So what is the outlet velocity in the y direction at location 2? This is coming in v and this is also going at v, so this velocity is actually v, correct? Understood? So this is minus m dot by 2 into v. So this product at this location is m dot by 2 into v actually. Clear? Plus at outlet 3, let us see what happens. At outlet 3, mass flow rate is again m dot by 2. Now can anyone tell me what is the velocity? Can anyone tell me at this control surface the fluid is crossing with a y direction of velocity? Yes, y component of velocity is present. Can anyone tell me what is the y component of velocity at this control point or at this control surface? See, y direction is this. Okay, if this is y direction, then what is the velocity here? Quick, come on, type in the chat box. It is minus v. And if you simplify this algebra, this is 0. Understood? You are actually not writing the fluid, not writing this, you are actually writing these fluid velocities, but those velocities are actually related to the control volumes. Okay, the velocities at which the particles are cutting the control surface is that velocity is what you are substituting here, and this is how you get this. Okay, normally if you know these equations very well, you will directly start with this equation, you will write this term, you will write this, that's it. Within one step you will write the answer, fx is equal to OAV square, fy is equal to 0, like that. Okay, that's the advantage of Reynolds transport theorem. Understood? In actual case, the equation is like this. This is normally when the control volume is in static conditions and all. Actually, this is relative velocities. Okay, and normally if the control volume is moving, then you have a relative velocity here. Okay, then this will be relative, this will be relative, this is also relative. That's it. Okay, because it's not always mandatory that the control volume stays at some location. The control volume can also move. So when control volume is moving, then definitely the fluid also moves. Okay, there is certain relative velocity between the control volume and the fluid. So it's actually in terms of relative velocities if control volumes are moving. Okay, in case of deformable control volumes, this is not 0. Okay, because with respect to time, this dV changes, we have to take that effect also. Normally in case of rocket analysis and all, normally let us suppose if some rocket is moving, okay, then what happens? The volume of the rocket keeps decreasing. You know stages in rockets. Normally if you have seen anytime ISRO real-time commands, they'll say first stage separation complete, second stage separation complete, these kind of things. Okay, so volume keeps changing for the control volume, so things change with time. Okay, because mass of the rocket also changes with time. So these things will actually create certain understandings. Okay, and I would like to solve one question because it's been some time since we solved questions. So let us solve this question before we leave. At what speed should the cart of the figure move away from the jet? So basically you have to calculate u. Okay, at what speed u? Fine. At what speed u this cart should move away from the jet to produce maximum power from the jet? Okay, so in order for this jet to produce maximum effect, what should be the speed at which you should move this? You all know one thing. I'll ask you one thing. Tell me. Let us suppose if this is a body, for example. If this is force F, and let us suppose because of this force F, this body is moving with velocity u. What is the power due to this force? There is a body. On this body, there is certain force, and because of this force, this body is moving at uniform velocity u, for example. Then what is this force actually? What is the power due to this force? What is the power due to this force? F into u, correct? Force into velocity. You know this, right? Simple mechanics. Okay, F into u. Now, if let us apply this and let us calculate certain interesting things here. So first of all, can I choose this as my control volume? Because something about fluids is changing in this region. Correct? Yes or no? Something about the fluids is actually changing in this region. So I am choosing this as my control volume. Okay? Because you should choose that volume in which the system is actually changing its properties. So this is the region in which fluid is changing its momentum. So that's my point of interest. Okay? Now, in case of rocket, reduction of mass or volume helps in increasing the velocity of escape. It happens, okay? And also we will plan the combustion accordingly, so that the combustion rate and combustion stages will plan accordingly, okay? Normally within the atmosphere, we will try to maintain the less velocity. We should reach escape velocity, but we will try to keep maintaining the less velocity because atmosphere exerts a drag on the rocket, okay? And drags beyond certain levels can actually affect the materials, okay? So that's what we'll see. As we go high, we keep on accelerating because the atmospheric drag reduces, okay? We'll see some important discussion in compressible flows regarding this, okay? Now, if you see, you know, sigma F acting on fluid is equal to m dot V relative at the outlet minus m dot V relative at the inlet actually here, okay? So this is at the inlet. Now if you see clearly, this is also moving with mass. So the cart is actually moving in the x direction. You see velocity is given in this direction because this wheels has to stay on the ground at any time. Okay, so we have to calculate the power exerted by the jet to be maximum. Okay, so if you take in x direction, sigma fx on cart, this is equal to m dot vx relative, v relative in the x direction in the inlet minus m dot v relative summation. Okay, this is also summation, v relative of in the x direction at the outlet. So this is what you have, because I have changed, this is on fluid, so this is on cart. So let us see, sigma fx on cart, fx for example is equal to, at the inlet, you can see at the inlet to this control surface, this is coming with velocity v, but this control volume is moving with velocity u. That means since this control volume it's attached to this cart, the control volume is also moving with velocity u. If fluid is moving at velocity v and if the control volume is also moving with velocity u, then what is the effective velocity at which this enters? Can anyone tell me? Let us suppose here this mass flow rate is OAV. Is it possible for the complete mass to enter this control volume? It's not possible, right? Because when this mass tries to travel, this control volume also shifts by certain amount. So therefore this mass which is flowing here effectively into the control volume is rho area of the jet into v minus u. So this is the mass flow rate which is actually flowing inside. Okay, multiplied with velocity relative in the x direction is nothing but v minus u. Okay, this is the case. Is there any other inlet? No, there is no other inlet. So the fluid actually slides smoothly again. There is no friction. So if this is v minus u, this is also v minus u. Anyway, we are interested only in the x directions. So let us see certain things. So now, for example, you take this x and this y, for example, then you can see at this point you have this x direction and y direction. For example, this is inclined at an angle theta, then this is x direction and this is y direction. So this is at inlet minus at the outlets. At the outlet, so how are we considering v minus u? Because the relative velocity at this interface is v minus u. Okay, got it? At this interface, the velocity at which the cart is moving, at which the fluid is actually entering the control surface is actually v minus u. Clear? That's why. Okay, because it's relative velocity actually, so v r should be relative in all the cases. Is this clear to you? Yes or no? So please type in the chat box. Is this understandable? Yes? Why not u minus v? Okay, got it. Why I'm taking v? That's your question. Okay, so why not u minus v? Try to understand one thing. This jet is moving with v. This cart is moving with u. If u is greater than v, can the fluid get in contact with the cart anytime? Let us suppose I am chasing. Okay, this is my fluid, this is my cart. If cart is moving fast and fluid is moving slow, then at any time can the contact between fluid and cart happen? No. Okay, so that's why definitely u has to be less. Okay, that's it. Clear? So let's see. This is v minus u. Okay, till here it's clear. Minus. Now coming to this, guys. At outlet, fluid is cutting the control surface at two outlets. This is outlet 2 and this is outlet 3. For example, these are the two outlets. Then m dot at this outlet is half of this into, if this angle is theta, x component of velocity is actually positive in this case. Okay, so v minus u cos theta. Okay, so this is v minus u cos theta plus, you need not be sorry here. You can ask any questions. Okay, it doesn't matter. Okay, you can always ask me. Let us suppose if somewhere if I write 2 plus 3 is equal to 5 and if you don't understand it, you can still, you deserve all the rights to ask me. Okay, I'll explain you and I deserve all the responsibility to say you. Fine, it's okay. So see here, this is v minus u cos theta plus, coming to this guy at point 3, what happens? Rho a v minus u by 2. This is the mass flow rate which is also causing, but can anyone tell me what is the x component of velocity here in this case? If this is theta, then definitely this is theta between plane and horizontal. So what is this? Same term with a minus sign. Yes or no?
it is the same term with a minus sign actually. Correct? With a minus sign, the same term will actually come. Correct? This is minus of v minus u cos theta again. Right? So minus v minus u cos theta. So clearly this angle theta is not given because these two terms gets cancelled each other because they are mathematically same. Okay, with a minus sign, these two terms will actually get cancelled out. If they get cancelled out, so this is the force acting on the cart in the x direction. So therefore, power is equal to force acting in the x direction into velocity in the x direction, velocity of the cart in x. Okay, so this is velocity of the cart into x direction. Please make sure if cart is moving in a particular direction, you should always keep the force in the same direction. Okay, F dot V is actually power. Okay, normally this is a scalars, but actually if you see power, this is force dotted with velocity. And if you want to write this as magnitude of force into magnitude of velocity and cos theta, definitely if you want to write this formula as this should be 1, which means theta should be 0, which means these two should act in the same direction. Means velocity of the cart should be in the same direction as that of the force actually. Clear? Then anyway, this is simple bit of dot product. Now P is equal to Fx on the cart is rho aj v minus u whole square into velocity of the cart. So cart is moving at velocity u. This is the expression for the power. Okay. Now try to understand one thing. In this expression, density of the fluid is constant, area of jet is constant, v is constant, u is the only variable. If I want maximum or minimum of any function, in maths you might have studied. So if you want to calculate maximum or minimum of any function, what is the thing you have to do? Tell me, what's the thing you have to do here? If you want to calculate maximum or minimum of any function, then what you have to do here? What you have to do? Differentiate, right? Yeah, we have to differentiate. So for maximum P, we have to done this stuff a lot of times. dP by du has to be 0. So this implies d by du of this rho aj v minus u whole square u is equal to 0. And clearly you can understand these guys are constants, you can eliminate them. So differentiation of these terms, v minus u whole square into derivative of second term plus second term into derivative of first into inner derivative, because this minus 1 is due to this minus u. Okay. Now if you simplify this, since v is not equal to u, you can cancel this term. So v minus u minus 2 times of u is equal to 0. So u is equal to v by 3. Means you should actually move the cart at 1/3 velocity of the jet so that the power supplied to the jet will be maximum. Clear? You can ask me, how do you know this is maximum? It can be minimum also. Okay. If you calculate second derivative, you understand the second derivative at this value of u is going to be negative. Okay. So that the power is maximum. Do you know why this first derivative has to be 0, second derivative has to be positive, second derivative has to be negative? Do you know why they should happen? You know it happens by default, but do you know why? If first derivative is 0, do you know, for example, why this second derivative test? If first derivative is 0, you will get a stationary point. At that stationary point, only if the second derivative is 0, you will have a maximum. Correct? Do you know? Okay, Ranjit. In maxima and minima concept, do you know why if the second derivative is positive, you will have a minimum, and why if the second derivative is greater than 0, positive, you will have a minimum? Do you know why second derivative negative gives you maximum? Why second derivative positive gives you minimum? Second derivative equal to 0 is saddle point. All these things, slopes and all tangents, if you do, you can understand clearly. Okay, but anyway, we'll find that at some time. Maybe it's okay if you don't know, then we'll see it sometime later. Maybe in this course, if you find some time, we'll see. So u is equal to v by 3 actually. Okay, so this is the velocity. So u is equal to v by 3. You see, it's very simple. Okay, writing these equations are all for your understanding. If I know these expressions, the first thing I'll be writing is this equation, then second equation is this. That's it. Okay, fine. If you see, then u should be v by 3. So if this is 30, then this should be 10. That's it. Okay, jet velocity is given 30, so 30 by 3 is 10. Clear? Did you all understand the Reynolds transport theorem correctly? And did you all understand what are the conceptual mistakes you are doing for past few days? Okay, velocities are actually the locations of the points where the fluid is actually crossing the control volume. Okay. Yes, correct above. Okay, basically you take a convex curve, and if you take the tangents and all, you can see second derivative negative gives you maximum. Okay, fine. I think we have crossed time again, so I was not able to solve Navier-Stokes. Guys, before going, I would like to make some small announcement. You can see, normally if you this question is also a good question. I'll give you this as homework. Okay, so please try this as homework. This can be solved using linear momentum equation. Okay, so this can be solved using linear momentum equation. Similarly, if you apply small energy balance for this, this is also homework. If you solve using energy balance, maybe in tomorrow's class I'll solve this. It's a very simple question actually. If you take this as a control volume and if you write your energy equation, you will get the answer. Okay. So anyway, these two are simple nice questions. You can try out them. The announcement that I want to make you is, see, normally today is 9th, I guess, if I'm not wrong. Today is 9th, na? Yeah, 9th October. Get 9th. Yeah, today is 9th. No, 8th, na? Today is 8th. Yeah. Thank God. Today is 8th. Fine. 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th. These are the days in which I have to close the fluid mechanics, out of which here to here it's holidays. So today's class is done. Tomorrow I'll take the class. 16, 17, 18 also I'll take the class. If you are okay, can I take one extra class on 15th? Can I take an extra class on 15th? Because I think if I want to explain some nice concepts, non-dimensionalization and all in boundary layers, I think I need one extra lecture. Okay. If I want to teach only mechanical syllabus, I need not take an extra class. I can close by here. Okay. But if I want to explain you potential flows in potential flows in using complex numbers. Okay. Anyway, potential flows using complex, you have the thing in the Gate English channel. You have the videos. So please go there. If you need any kind of help from there, you can go there. And this 15th I'm going to plan one extra class. Okay, so maybe tomorrow we'll close this Navier-Stokes and also some bit of introduction to external flows. Here we'll teach external, then turbulent and dimensional, and here we can go for potential flows and compressible flows a bit. Last class we'll look at turbo machines. Yeah, same timings. Okay, fine, only on 15th. But here I cannot take actually because I have some other, I actually planned my travel, so I cannot take unfortunately. So because flight tickets all are done, so can I take one extra class on 15th actually? If you want to learn, definitely we have Sundays as buffers. At any Sunday we can take a class. Okay, no issue. Like for example, again 19th I think Saturday, 20th there is Sunday again, right? So we can plan one extra class if needed, if you feel that we should have one. I'm always happy to teach. Okay, so we can do. Clear? So this is what I'm planning. Only on 15th, maybe one extra class is needed to cover certain things. Okay. Meanwhile, so please look at this control volume analysis and potential flows from that channel. Okay, it would be helpful for you. Fine. Saturday, Sunday you have maths classes. Such a fine. Okay. Fine. We can find out sometime. Okay. We can meet at any time on YouTube. No issue. Right. Okay, so fine. Then we can see there are some nice questions actually which I thought of covering today, but I couldn't because of this RTT. Our Telegram channel is this. Okay, so that's the Telegram channel, and basically we have seen today majorly RTT and also applications of Bernoullis. Okay, so apps of Bernoullis is what we have seen. Okay, so that's my Telegram ID. If you feel I can help you out somewhere, you can join me. Okay, and yeah, that's it. Then we'll wind up the session. Thank you. Okay, are you all understanding the things, guys? Are you all getting some good concepts, good logics, good understandings of the subject? Did you feel this session helpful? Did you learn something from this? Yes? Okay, fine. Then we'll meet tomorrow. We'll see angular momentum, which is left, and then we'll see Navier-Stokes. Okay? Yeah, we'll touch up tomorrow, definitely. Okay? Fine then. Yeah, take care. More helpful than comprehensive. Fine, thank you. Okay, so we'll meet on tomorrow at 7:30 a.m. and we'll continue our discussion. Yeah, thank you guys. Take care. Okay, bye. Take care.